millions of years ago already, people were cutting. And they were using tools for that. And today we still find those tools, like you see here an example, and we recognize them for what they are, cutting tools. And why do we recognize that thing is a cutting tool? Due to the shape, the form, the geometry. And that's the subject of today, cutting geometries. Why do we use them? How do they work? And sometimes I wonder, you know, millions of years after this guy was cutting, archaeologists, they still find his tools and they recognize it. I wonder if archaeologists would do excavations, let's say in Fagersta in Sweden, where we have a main production unit, millions of years from now, what would they find back? And would they still recognize it as cutting tools of the 21st century? I wonder. But anyway, it's about geometry. Geometry, the role geometry plays in a machinability equation. How do we work with them? Why do we use it? My name is Patrick de Vos, and I'm going to talk about that today with you for roughly 45 minutes. It's not a long time, but anyway, we try to take the good things out of that total chapter. And of course, again, I'm not alone here. I'm together with my colleagues behind the camera, Alesia, Viju, Margarita, and Olivier. They do the magic work, as I always say it, that all of these things are happening. And you know, in preparing this, I had some communication with people on social media and stuff. And one of those people is a guy called Sam Langford. He calls himself a problem solver when it comes to CNC machining. And I think he made such a brilliant statement on social media. I asked him if I could use it here. He said, a brilliant geometry won't give a good result if you aren't using it properly. Obviously. But the wrong geometry has limited or no potential, no matter how hard you try to make it work. That statement comes from Sam, and I think it's spot on. It's exactly what we talk about. Now, today we are going to talk about the physical insights around geometries, not especially the calculations, the mathematics, because I think nowadays there's no use anymore, there's no need anymore, sorry, to talk about formulas and so on. Today we have modern things to help us there. We have things like what we refer to in SECO as the Suggest software that helps us to make all the calculations. But you know, calculations is one thing, but in every software there is a possibility that there are bugs falsifying the calculations. And what I think is very important for us is that we have insight in the matter and that we understand in a physical perspective what is ongoing. That in the case there is a bug that falsifies the result of the calculations, that we recognize it and that we can take proper actions for that. The background is a machinability model we use. Machining is a process where we deform material until it shears off and is evacuated under the forms of ships. That's the definition of a machining process. And machining is not the same as cutting. And I know the English word metal cutting is a bit confusing. Machining is not cutting like the cutting we do at home in the kitchen. Machining, again, is basically a deformation process where we deform material so much it shears off. And that process, from a physical perspective, understanding it, in the book of understanding, there are quite a lot of chapters. There's the mechanical chapter and the thermodynamic chapter and so on. What today I want to do with you is to try to define together with you the variable called cutting geometry, how that interferes or how that determines the different types of phenomena we are seeing in or around the machining process. And as I said, machining, you have all those chapters in that book of applied machining physics. There are variables interfering. There are variables in the equation. Variables coming from the process. That's the gray part here, the left part in this picture. There we think like, there we find things like what conditions, in what conditions are we doing the process, the cutting data we use, the tool concept, all that type of stuff. And there is the right side, the blue side in the picture here. That is the features or the attributes from a cutting tool that has to take care of this situation in an effective and an efficient manner. And then we talk about cutting materials and coatings and geometries, the subject of today. And knowing if we solve the machining equation in a good way is today still a rather pragmatic thing. It's basically a people thing. It's people observing the process and using their experience, their expertise to feel if things are going well. Of course, you can also turn to the cutting tool, and a cutting tool it tells you a lot about how the process went. But anyway, we want to solve an equation here. We have an equation we refer to as the machinability equation, where we have different variables. We bring together, and all those variables, those attributes together form a cutting tool. And with that cutting tool, we are going to do the machining process in the best way possible. Now, if we talk about cutting tool attributes, there are two big families. One family refers to the cutting materials, carbide, PCBN, ceramics, cutting materials, and a very important part there is also the coatings. That's the material side. The other side is the geometry side. And if we talk about geometries, first we have to be a little bit specific here. We refer to things, to some geometries we call macro geometries, and other things we call microgeometries. Now, what do we talk about exactly here? The macrogeometries refer basically to the cutting-edge support. If we talk about a tooling system where we have inserts as the cutting part and a tool holder as the support part, the macrogeometry refers to the tool holder. How is a cutting edge, how is an insert positioned globally compared to the process? Microgeometry, that's when we focus in, when we dive into the actual cutting edge, the actual part doing the machining. How does that look? That is what we refer to as the microgeometry. So we have cutting materials, that's one chapter, and we have geometries, that's another chapter, another family of variables. And we have cutting conditions. Now, cutting conditions, they kind of form the connection. I mean with that, imagine you decided to go for a certain cutting material, whatever cutting material, and most of the time the selection of cutting materials is made mainly in function of the workpiece material that needs to be machined. Mainly. But those two needs to be connected to each other. Workpiece material with its properties and cutting material with its features and properties, they are going to kind of work together in a certain way. And in a certain way that is defined by a cutting condition. And if we talk about cutting conditions, there are three major groups of cutting conditions. In this picture referred to as A, B, and C. Now I wonder, and perhaps you would like to give me your opinion, your feedback. Traditionally, if we talk about cutting conditions, we talk about cutting speeds, we talk about feeds, and we talk about depths of cut. That's the three big groups of cutting conditions. And here you have A, B, C in the picture. Now, based on your experience, on your knowledge, what do you think? Where do I put cutting speed? In A, in B, or in C? Where do I put the feet? In A, B, or C? Where do I put the depths of cut? In A, B, or C? With other words, the three traditional cutting conditions are connecting factors, but what are they connecting? That's the question here. I give you some seconds to make up your mind. What is A? Cutting speed, feet, or depth of cut. What is B? Cutting speed, feet, or depth of cut. And the same final question for C. Put it in the comments, in the chat. I'm very interested to hear what you think about this. Anyway, I don't want to send you home without answering the question. Mainly, cutting speed forms the connection between materials. Cutting speed is a material connecting thing. Connecting workpiece material with cutting material. Depth of cut is, together with feet, connecting geometries with type of applications. And type of applications can be different types of applications. It can be geometrical, milling, turning, face milling, square shoulder milling, that type of things. It can be technological, high feed machining, high performance machining, that type of thing. And it can be economical application. I want to have the highest possible productivity. I want to have the highest possible cost savings, whatever. This is mainly how we use cutting conditions to connect elements. And if you think on that, you know, a lot of people, if I would ask you what is most important, cutting materials or cutting geometries, now I know machining people, they will say both, but imagine I force you, I say you must take one as a priority, most probably you will say cutting speed, cutting materials. And cutting materials are indeed important, but if you think on the impact of cutting materials, different cutting materials will impact mainly tool life. If you improve your cutting material, if you improve the features of the cutting material you use, you will take advantage of a better tool life. Now, cutting geometries, if you think on it, if you modify cutting geometries, if you play with cutting geometries, what you influence then is the total process. And millions of years ago, people already recognized that. It's not the type of stone you use, it's the form of the stone which is important. The total effectiveness, the total efficiency of the entire machining process, including the tool life of the tool you use, is determined by cutting geometry. Seen like that, I think it's only fair if we prioritize cutting geometries. And again, I don't say cutting materials are not important. Of course they are important, but the cutting geometry is perhaps a little bit more important. Now, if we talk about geometries, it's important that we know what we talk about, because lots of words are used here. Now, geometry attributes, geometry features on a cutting tool, and I take here as an example an insert type cutting tool, as it is called. A cutting tool where you have an insert that offers the cutting edges to the operation, and that insert is put in a tool holder, and the tool holder is the support and the connection to the machine tool. Now, I know quite a lot of tools today are also solid carbide type of tools. Think on twist drills, think on solid carbide milling cutters. But basically, we find the two same things there. You have a support part and you have a cutting part, but there they are in one. But for a pure understanding, it's easier to talk about insert type tools. Now, if you look to a tool from a geometrical perspective, if you look to an insert from a geometrical perspective, first of all, you have the global shape and dimensions. Shape is square, triangular, whatever. That's what we refer to as global shape, and the global dimensions are how big is this thing? How long is the cutting edge? How thick is the insert? And so on and so forth. Global shape, global dimensions. You also have the cutting edge line type and positioning. Is your cutting edge a straight line or a curved line? And how is it positioned compared to the operation? That's what we refer to as the cutting edge line type, straight or curved, and positioning. Another part, when we talk about geometries, another element there is the cutting edge geometry. How does the actual cutting edge looks? Nearly, I could say, on a micro scale. You have the rake face positioning and geometry. The rake face is that part of a tool where the ship, as it is formed, will glide over and be evacuated. That's referred to as the rake face. You have the cutting point. The cutting point is where the main cutting edge ends in the operation. That's referred to as the cutting point. Some people call it the nose, but I think cutting point is a better word. Again, here you have type, position, and geometry. And finally, you have the clearance phase, positioning, and geometry. The clearance phase is the part under the cutting edge that needs or that is going to support the cutting edge. These are the main geometrical attributes when we talk about a microgeometry, the geometry that relates to the actual cutting edge. Now there's one I haven't mentioned yet, and I put it here a bit in a different color because it's one of those things, to tell you the truth, we are not yet absolutely sure we fully understand the role of this thing. It's called the T-land geometry. It's something we use since a long time, but still there are some question marks. The T-land geometry is kind of the thing we find between the actual cutting edge, the true cutting edge, and the rake face. Somehow we need to connect those two. And the way we connect the cutting edge to a rake face, we refer to that as a T-land geometry. It's the thing, you know, perhaps some of you remember in the past when you were grinding your own cutting tools, and after the grinding you had the little polishing stone in your pocket, and then you were doing some things on a cutting edge to make it really effective. Now that thing you were doing on a cutting edge, that is what we refer to nowadays as the T-land geometry. Now, each of these features serves a purpose. We don't just do it for the fun. And interesting, perhaps, again, what is your opinion? What we want to influence with cutting geometries is tool life, ship control, edge stability, and micro-cutting ability. The question is, out of these four attributes, cutting edge line, type and positioning, cutting edge geometry, T-land geometry, and rake face positioning and geometry, which of these four is the main one that will influence tool life? Which of these four is the main one that will influence ship control? Which of the four will mainly influence edge stability? Edge stability, perhaps I have to specify, edge stability, what we mean with it is the effective time a cutting edge keeps its original cutting ability. One could say it's kind of wear resistance to some extent. And fourthly, micro-cutting ability. Which of these geometries do we need if we want to work with very small cutting conditions? Again, I'm looking forward to find your answers in comments. And answer perhaps with T, C, E, and M, and add a figure. So if you think that tool life is mainly influenced by the cutting edge line type and positioning, put then in comments T1. And if you think ship control is mainly influenced by cutting edge geometry, put C2, and so on and so forth. It's for me interesting. I'm always like to do this kind of little inquiries, you know, to feel a little bit, to learn a little bit how people think about these things. Now, some things related to this. The global shape of an insert, if you allow me to call it like that, I could say the global shape as it is defined by the rake face, the clearance face, and the point is having a big impact on the total strength of the tool. The bigger the what we will refer later on as the point angle, the bigger the point angle the cutting tool has, the higher the overall strength of the tool is. Strength in a sense of resistance for breakage. Cutting edge length. Why is cutting edge length important? Well, very simple. Cutting edge length, the length of the cutting edge determines the maximum depth of cut you can use the tool with. With a tool with a bigger cutting edge, you can use a bigger depth of cut. Rather straightforward. There are, however, limits to that, because somewhere is looking around the corner cutting security here, cutting safety. That's why most of the time we will never ever use a cutting tool with the full cutting edge in cut. We will always limit it a little bit. That's kind of engineering thinking, you know, security thinking. How far can I go, but I want to make sure that the thing doesn't break. I have been talking so far about main cutting edge or primary cutting edge. I'm pretty sure some of you were thinking now, yeah, primary, if there is a primary, there must be a secondary. Indeed, there is. The primary cutting edge of a cutting tool is the cutting edge doing the actual machining. That primary cutting edge ends in the cutting point. And if you move over the cutting point, you end up at what is referred to as the secondary cutting edge. Some people, but that's a little bit commercial terminology, some people refer to the secondary cutting edge as the scraper cutting edge, the wiper cutting edge, and that finds its origin in, as a matter of fact, that the surface finish of the machine surface is influenced by a big number of things, but mainly, I would say, or mainly is perhaps exaggerating, but to a big extent, is depending also on the positioning of the secondary cutting edge. As you can see here in the example, we have a cutting tool with a very specific secondary cutting edge geometry, and that gives us, with the same cutting conditions, a much better surface finish. So the quality of the machine surface is influenced by, we will see later on, the point geometry and the feed, but also by the secondary cutting edge. There are limits, because if you are too progressive with your secondary cutting edges to improve your surface roughnesses really to an as high as possible level, you end up with a cutting tool which is very sensitive for vibrations. And that, of course, is a limiting factor then. Point geometries, how is the point looking? Is it a radius? Is it a chamfer? Is it a combination of things? And how big is it? Is influencing kind of the strength of the point. And influencing the strength of the point gives you an ability to use higher cutting conditions, because higher strength means that you can go higher in feet and depth of cut. You can see it in a different way also. If you go for strong points, big radiuses, for instance, to make it work, you also need a minimum depth of cut and feed to make it work. And I show you in a few minutes some videos to illustrate that. So this is a thing that goes from two sides. Big points, strong points, give you the possibility to work with big depths of cuts and feed. But to make a strong point work, you also need big depths of cuts and feeds. So strong points limit the ability of a cutting tool to work with small depths of cuts and feed, what we refer to as micromachining. Here you see an example about different geometries of a point. You see 2 times the same cutting point, the same dimensions, same type of point, but the geometry is modified, and you see how ships which are formed are different. Same tool, same cutting conditions, but the geometry of the point is slightly different, and as a result we see different ship formation. So later on we will talk about ship formation. Don't forget that the actual point of a tool plays a role there. Edge line, rake, and clearance phase position. And here we are in the traditional geometrical stuff. I can go fast here. I suppose you are all familiar with what is referred to as the rake angle, the clearance angle, the edge angle, the cutting edge angle, and all that type of thing. That is how we define edge lines, rake, and clearance phase positions. This is a bit the macro geometrical side of it. And this type of geometry we find in all tools. This basic definition, if you have a turning tool or a milling tool or a drill or a reamer or whatever, you always find these elements back. Rake phase, clearance phase, top angle, point angle, edge angle, wedge angle, and so on and so forth. We use these things to give a cutting edge line a positioning which we refer to as the inclination. The inclination is how, compared to the cutting direction, we position the cutting edge angle. We refer to this as the inclination angle. In milling cutters, we call it the helix angle. That's just words, of course. We use this geometrical element for two things. We want to influence ship formation, and we want to influence pressure on cutting edges. So we want to influence by reducing the pressure on a cutting edge. We want to influence tool life, and on the other hand, by influencing how ships are formed and mainly evacuated, we want to influence the reliability of the process. Another thing we use to define how cutting edges are positioned is called the cutting edge angle. The cutting edge angle positions the cutting edge compared to the feet. So inclination angle is positioning compared to cutting speed. The lead angle or the cutting edge angle is the positioning of a cutting edge compared to the feet we use the tool with. Also here, cutting edge angles are used for ship formation purposes, to influence ship formation in such a way the ships are more favorable, or to influence the pressure on the cutting edge. With other words, we want to influence tool life. Then you have the rake phase geometry, the actual rake phase. How does it look? And there are lots of elements here. What we really want to do with rake phase geometry is that is influencing how a ship is formed and evacuated. And basically, based on all kinds of geometrical stuff, and you know, some of these inserts nowadays, if you look at it, it looks very, very sophisticated, very beautiful. The question is, is all of these things really needed or not? But that's a bit of another question. Let's say today that okay, we form a rake phase in such a way that it performs in all kinds of different situations in the best way possible when we focus on ship formation and evacuation. In this respect, we talk about sharp geometries, medium geometries, and rough geometries. That basically refers to the application. A fine geometry, a sharp geometry is for finishing, a medium geometry is for the average operation, and a strong geometry, a rough geometry is for roughing applications. Finishing roughing is defined by combinations of feet and depth of cut. And it's visualized by what you see here behind me for the moment, the so-called shipbreaking diagrams. One of the previous live events we had, we were talking noticeable on shipbreaking geometries. Next to that, there are lots of other considerations. The rake face needs to give support when you put the insert in the tool. It has to reduce cutting forces where possible. It has to help us to keep thermal effects under control, and so on. There are quite a lot of considerations here. And in the end, what you can see here with all the different videos, you end up with tools with all kinds of rake face geometries, and each rake face geometries is appropriate to be used in a certain type of application. Main cutting condition considerations related to this geometrical attribute is depths of cuts and feeds. Micro cutting edge the actual cutting edge, how does it look? Is it sharp? Is it round? Careful here, we talk about microns. Cutting edge geometry, some people call it the edge treatment, edge reinforcement, some people refer to it. This has to do with how does the actual cutting edge looks, and you have to see it like that the actual process, and I try to visualize that here with micro videos where you see the actual cutting edge truly cutting, and so you have the true contact between undeformed material and you deform it, and deformed material, that's on the cutting edge. And to make that happen in the best possible way, we work with cutting edge geometries. A cutting edge geometry is very small, and that's what I try to illustrate here with the animation to the right, that as a tool wears out, after a while, after a number of minutes in cutting, you kind of, while you are cutting, you do destroy, or destroy, perhaps I should not use the word destroy, I should use the word modify. The micro cutting edge geometry is changing while you are cutting. And that has consequences. It would take us too far in today's limited time which we have available to dive into this. But if there are people here really interested in this effect, I can always share some extra information on this. Just let me know, because this is truly a very interesting subject. Now, these microgeometries, they play a very important role when you talk about tool life. Sharper cutting edges gives you longer tool life. The risk is that you have troubles with edge stability. That's a bit the thing you have to worry about. But if possible, if edge stability is not an issue for you, you should use as sharp as possible cutting edges if you like to have long tool life. Edge sharpness also has a big impact on surface roughness, and here the picture is not so clear because there are certain edge sharpnesses that gives you best surface roughness, best surface finish. If your edge sharpness is too sharp, one could say, you lose edge stability, and that will be reflected in the fact that there will be shipping on a cutting edge, and that will deteriorate your surface roughness. If your edge is too strong, not sharp enough, you will have potentially issues with micro vibrations, and that again is going to influence your surface roughness. So it's a very kind of narrow window we are in here. Now, the cutting behavior, because so far what I have been doing is trying to define all the different, attributes in that big, all-included word, the cutting geometry. Here and there I drew already some connections for you on how certain of these things relate to how we use the tool and how the tool behaves and so on. But I think it's important to finish here also with letting you understand really fully how geometries influence the cutting process. I start here, and let's focus on the movie. You see here a high-speed movie, micro movie, or micro picture. And you see here a so-called neutral cutting geometry. The rake angle is 0. And if a tool has a rake angle, see the red line here and compare that with the cutting direction. The angle between the red line and the cutting direction is 90 degrees. That's what we call neutral cutting. The effective rake in such a case is 0 degrees. And try to visualize how you see a ship being formed. It's a certain process of deformation, shearing off. And you have a tool here with a certain strength. That's the blue arrow, kind of. And the cutting process itself is putting loads on the cutting edge, which is represented here by the red arrow. And there is balance. It works. Because the whole machining thing is a balancing exercise in the end, It's balancing the ability of a tool to cut with the demands which are put on the tool to do the actual application. We have balance here. Now, compared to this neutral cutting, you can have a situation where we refer the geometry as a positive cutting geometry. The angle between the cutting direction and the cutting line, the cutting rake, is bigger than 90 degrees. We refer this, that's how we agreed upon it. We call this positive cutting. We have a positive effective rake. And you see here quite a different process now. You see here a situation where the cutting is much more, cutting. That means that all the loads that are going to act on the tool are on a lower level. The little red arrow is smaller. But on the other hand, you have a cutting tool which is sharper, and that makes it, let's say, more fragile, less strong. So we have to be more careful with the tool. And in case of positive cutting, again, it's about finding a new balance point. A balance where the loads acting on a tool are lower, but the ability for the tool to withstand the loads is also on a lower level. Now, why would I like to do positive cutting? The main thing why I want to do it is situations where, by definition, by the nature of the application, the loads which are going to act on a cutting tool are lower. Think on smaller depths of cuts, smaller feeds, softer workpiece materials, where there is less heat generated when you do machining. All those type of things, the so-called easy cutting applications, are applications where our thoughts have to go into the direction of positive cutting. But you have to be careful and realize that the tool we use to do this is also a weaker cutting tool. It's again, make sure you have the correct balance. The opposite is negative cutting. Negative cutting is a situation where, on purpose, I make a tool negative cutting. The angle between the cutting direction and the rake face is lesser than 90 degrees. That is what we refer to as negative rakes, negative cutting. And here we have a bit the opposite. If we have situations where we know, or where, by the way we define the application, we know that the loads which are going to act on a cutting tool are going to be high to very high. I'm thinking on big depths of cut, big feeds, harder workpiece materials, more heat generated during the machining, workpiece materials with difficult structures, material structures, all those things we all know about, they make machining more difficult. That's a situation where, from a geometrical perspective, we have to find an answer, and the answer is more negative cutting. But again, in the end, it's about finding a new balance. Now we have to find a balance between a strong tool, but the situation in which we will use it needs a strong tool, because the loads acting on a tool will be higher. Here again, it's about finding that new balance point we need to make the thing work. So if you look to geometries, in the end it comes down to that there are three families. You have a situation where we prefer positive cutting, because our estimation of the cutting environment is that positive cutting would be favorable for the application itself. And then we need a tool with the appropriate features to make it happen. In other applications, our estimation will go in the other direction. We will think in terms of, oops, this is difficult. We are going to have high loads acting on a cutting edge. We need to make sure that the cutting edge can take it, can handle it. And that's when we move into the direction of negative cutting. So geometries are there to give us the ability to create a positive cutting machining operation or a negative cutting machining operation, or perhaps not that we created, but that we need to have an answer on a situation where our estimation is that this will be easy machining or this will be more difficult machining. That's in the end what we do with geometries. Now we have to be careful with geometries, and I try to illustrate that with here 4 pictures. I think the video itself is perhaps not so clear, but anyway. You see here 4 times the same cutting tool with the same geometry, rake face geometry, cutting edge geometry, cutting edge line, everything is the same, but I use the tool with from left to right, a big feet, a smaller feet, and the one to the right is very small feet. And what you see is, and this is a very interesting thing, for some people it's strange, but I think it's interesting, because we can do interesting things with this, that is, depending on the feet with which you use a certain cutting edge, how a cutting edge reacts from a geometrical perspective is influenced by the cutting conditions you use. If you look to the tool to the left, you see a tool with a big feet, and the tool acts kind of like a positive cutting tool. If you go directly to the situation to the right, where we use the same tool but with a very small feet, well, there you have now a tool that acts, I don't say it becomes, but it acts, it reacts like a negative tool. And this phenomenon, especially in workpiece materials like titanium alloys and superalloys and so on, you can do strange things once you have this insight in a process. That this, whatever geometry you use, how the geometry transforms into cutting behavior is influenced by the cutting conditions. That makes that the effect of a geometry on the process is a variable that is depending on its turn on another variable, for instance, in this example, the feet. Cutting geometries for sure influence cutting behavior in a mechanical way. The cutting forces that we will see or observe during a machining process. You see here the famous Kinzel formula. I said in the beginning we are not going to talk about mathematics, and we are not. But I use the formula here to let you understand that in that formula defined by that German gentleman Kinzel, where he says, I can define cutting forces as a relation of the workpiece material, the cutting conditions we use, and another of other variables here represented by the correction factors at the end. In those correction factors we need to take into account to define cutting are also the cutting geometrical features, the rake angle, the clearance angle, all that type of thing. So cutting forces are influenced by geometries. Heat generation is influenced by geometries. You see here some examples of different tools with different geometries. The blue, yellow and red line are different geometries, and we see how cutting temperatures are influenced by cutting geometry, which makes sense, because the sharper a cutting edge, the easier it cuts, the lesser it has to deform material. And when there is less deformation, there is less heat generation. And when there is less heat generation, the temperatures are lower. So temperatures are influenced also by the cutting geometry. Surface roughnesses, I already mentioned about the cutting point and the secondary cutting edge. The surface roughness of a machine surface is very clearly influenced by geometrical considerations. And that brings me to the summary. We went fast, but I hope not too fast. I made a statement 20 minutes ago. I said the cutting material attributes determine tool life. The cutting geometry attributes determine the effectiveness and efficiency of the entire process. I hope with some of the elements I mentioned here, I kind of convinced you of that. That how a tool is working really, how the machining process actually is developing, the physics of it, is very strongly depending on the geometry of the tool you use. The speed with which you do machining, that's the cutting speed. That's tool life, that's cutting material. But how the process takes place, that's geometry. That's what I tried to tell you here. Now, I talked about effective geometries, important because when we talk about geometries, we talk about nominal geometries and effective geometries. Nominal is tool in hand. I have a tool in my hand, and I start to look at the shape, and I define angles. That's the nominal geometry. That's what you find in catalogs. This is a tool with a rake angle of 6 degrees or something like that. Effective geometries, that is the actual geometry as it will look like during machining. You remember a couple of minutes ago I told you that how a tool behaves, positive or negative cutting, is influenced, by instance, by the feed, but that's what we refer to here as the effective geometry. You can have a tool with one nominal geometry, but with a lot of effective geometries, depending on how you use the tool. And the effective geometry is depending on the tooling system you use, solid carbide or inserts, for instance. Is depending on the machining strategy you use. Is depending on the cutting conditions. So that's quite a chapter on its own. But it's important that you have to realize when you select a tool from a catalog, you select a tool with a nominal geometry. The way you use it will define the effective geometry. So one could say, the statement from San Lanford, the effectiveness of a tool, the effectiveness of a geometry is determined by the one using the tool, the operator. He determines if a tool cuts well. Cutting geometries have an impact on quite a lot of things. I give you an example here which people sometimes forget. If you do wear analysis, when we do, for instance, with customers what we refer to as a GTDA, a global tool deterioration analysis, where we look at used tools and try to put some logic in things. By the end of the exercise, of course, part of the answer that needs to be formulated is, okay, we see tools here with certain wear patterns, and if we don't like the wear patterns, how are we going to take care of it? Very traditional people say, we change the cutting materials. Tool wear is cutting materials. Yes, but not always. If your tool wear is of a type of where it's more breaking, then the answer is perhaps not cutting materials, but cutting geometries. So be a bit careful here. Geometry of cutting tools for those, I don't know if there are people listening here and they say, my big concern is the total operation, the production management, the production system, and people talking in those terminology, they very quickly start talking about that famous, notorious OEE, overall equipment efficiency. And then you see diagrams like the one you see here. Well, if you do small batch, what you see is if you start measuring that OEE in small batch, you see that a big part of the time losses is in the chapter of minor losses. Minor. Okay, it's just a word. And if you dive into, and if you look, why do you have minor losses? And then you end up in a technological chapter. What is making that now and then you have to stop the machine? And I don't know if it's clear on the screen for you, this diagram. If not, just let me know in the comments. I send you a big copy of this slide so you see it in real detail. Everything blue here are potential issues you can have during machining that will lead to a minor stop of the machine. And all the blue things refer to the geometry of a cutting tool. I had situations where I dare to make a statement that using the wrong geometry during machining makes or gives you a 25% loss in your OEE. Now, that's a firm statement to do. I do it here at the end also. I'm already a little bit over time, I see. But people, if this is what you interest a lot, also here leave me leave me a word, leave me a message in the chat, and we can dive into this, that I cannot just make the statement, but of course, yeah, give you the reasoning behind the statement also. We talked about geometries. I hope, with the examples I gave you, that I could, the statement I made, that the geometry is effective, the efficiency and the effectiveness of the total machining process or system, that I could perhaps not convince you, but at least make you think. Cutting materials are important. I'm the first one to admit that. But I think that cutting geometries are a little bit more important. Are there questions? I have to try to make the thing appear on the screen now with the questions. It's coming. Questions related to this? Ooh, that's quite a lot of questions, but good. Let's see how far we get. I have 10 minutes left. There is a question from Kevin, and his question is, does sealant touch the cutted material? Yes. The sealant touches the cutted material on the ship side, not on the machine surface side. I hope you understand what I mean with this. And the second part of his question is, does it influence the cutting heat? Yes, because it influences very strongly, but it's depending also on the feed you use. But leave that aside. The T-line geometry is affecting very strongly the deformation zone when you are machining. And most of the heat generated during machining is generated in the deformation zone. So it very strongly influences the cutting heat. That's why T-lands are having a very big effect on tool life also. It looks a minor thing, but it is very important. Then there is a question from Bivlia. I hope I pronounced that well. Why do we speak a lot about parameters of T-land only on CBN inserts? I don't know. Is it? Do we? I think we should talk about T-lands always. And I know, perhaps yes, perhaps I do understand, because the importance of a T-land in case of a CBN insert, or perhaps I should generalize a bit, also a ceramic insert, is perhaps even a little bit more important than it is in carbide. In carbide, when you make a mistake with the T-land geometry, the cutting material kind of can hide a bit the mistake you made. If you make a mistake in a CBN insert with a T-land geometry, and yeah, you are dead. That's perhaps why people discuss it more in case of CBN inserts. But again, I think we should talk about it in all types of cutting edges. For your information, also on milling cutters, also on solid carbide tools, also on drills, also on reamers, T-lands, whatever size or form or dimension they have, are for all cutting edges important. Then there is a question from Sashi, who's always in for the next session. I like Sashi, you know. He's asking, is the next session about micro-cutting geometry? No, sorry to disappoint you. Next session is on temperature, thermodynamic effects on cutting edges. But on the other hand, it's a very good suggestion to have a session on micro cutting or on micro machining in general, perhaps. Good suggestion, we take note of it. Thank you, Sashi. Then there are Marcus and a lot of other people want to have a copy. Okay, we take note of that, and we make sure that you leave your name or whatever and email or something that because I can say yes, of course we want to send you a copy, but yeah, we need to know where to send the copy to. You understand what I mean? So please leave behind data that we know where to send the information to. Next question from Morteza. Positive cutting wedge use when we need better cutting quality, which lead to less load and heat. Yes. I don't think that's a question, that's a statement, and that's a statement I full-heartedly agree with. Very correct statement. Then Marcus again. Is any of this information available online? Yes, there is, but there I have a look at my colleagues behind the cameras. They should help us in that, because this thing is recorded, so you find the recording here on all kinds of social media. You also find it on our website. There are quite a lot of material there also available. If you don't find what you need there, let me know. Perhaps I can help you with. And then there is, I'm not even going to try to pronounce that name, sorry for that, but that's a very, for me, difficult combination of letters. But somebody is asking if we are going should talk about cooling. Yes, we are. As I said, the next session is about thermodynamical considerations around machining, and logically, if you talk about that, you talk about cooling. So if you are interested in cooling and the effect of cooling, I would say make sure you join for the next session, which is somewhere next month. Next question from Mario. Is it right that your feet must be a bit higher than the T-land? Yes. Personally, but that's personally, I say your feet should be at least the T-land. Personally, I like to take it 1/3 bigger. If your T-land is 1/10 of a millimeter, I think the minimum feet you use the T-land, which should be 13/100 of a millimeter. Of course, this is also depending a bit on which type of T-land you have. I have to be careful with my answer here, not to make it too general. Let me say the statement you make here, Mario, is very correct. And the more you have a negative T-land, the correcter it becomes. If you have a positive T-land, it's not so important. But when you have negative T-lands, think especially on CBN inserts, where most of the T-lands are effectively negative, there indeed the feet must be bigger than the T-land. You can work with smaller feet, but you will be in for some very, very tough machining there. I have some time left. There is a question also. Which insert angle improved the ship breaking on steel? I would say mainly it's not an angle, it's mainly the rake face positioning and geometry. How does the rake face look? How is it positioned? With all the geometries, the shapes you find on a rake face, how big are they, how deep are they, how wide are they? With other words, what we refer to as the ship breaking geometry of a cutting edge. That is the major important for ship breaking. And then, okay, two more questions perhaps. One question is, somebody makes a statement, he says, some of the rake faces we see today on tools, they look very, very sophisticated. Is that science or marketing? Now, what should what should I answer here? I would say it's a lot of science, but could be here and there some marketing also. Yeah, that's the visual aspect. But I would say mainly rake faces, because rake faces are designed by trial and error. We take a geometry, we make ships, we see how the ships look, and then we try to have, based on the insight we have, okay, I see this type of ship, I want to modify it a bit like this, and that most probably I could do by modifying the rake face a bit like this and this and this, and then we try again. That's how we design rake faces nowadays. That in the end leads to very strange forms, but I admit sometimes it's a bit of marketing also. I hope that's an honest answer. You accept it for what it is. And then a last question, somebody asked, what is STEP? Yeah, that abbreviation thing, you know, everybody's using abbreviation. Sorry for it, I make the same mistake. In SICO we have a big number of programs, educational programs. And those things are referred to as the STEP programs we offer to the machining industry as education on machining science and technology. And the word STEP stands for SECO Technical Education Programs. So it's a collection of educational programs we run to distribute in the machining industry the knowledge, the expertise we have on machining processes, machining systems. Yeah, I have to stop here. My time is up. I hope it was an interesting hour. I hope I made you think a little bit about the importance of geometries. Perhaps that next time when you have to select a tool for a certain application, that you don't only spend time on cutting materials and the selection of cutting materials, but also think a little bit about the geometrical side of your selection. How does the tool look? What are the dimensions? Because the process itself is very strongly influenced by the geometry. And I can only repeat the statement made by Sam. If your geometry is wrong, now no matter how hard you try, you can't make it a good machining process. It's as simple as that. I hope it was interesting. I'm looking forward to see you next time. Next time we are going to talk about thermodynamical effects during machining. Machining is a deformation process. If you deform material, heat is generated. If you allow heat to concentrate, it increases the temperature where the heat is concentrated. And we undergo that in machining, and we talk about the cutting temperatures. A very important thing in machining, cutting temperatures and how they affect the actual process. What are the consequences of cutting temperatures? Looking forward to see you then. In the meantime, all questions, remarks, put them in comments. I promise you I come back to it. If you want extra information to be sent, no worries, I send, but then you need to tell me where to send it to. Thank you very much. Looking forward to see you next time.